Yes, okay. I'm John, an old YouTuber. I update my PDF and read lists. It's 10:30 Friday evening. It's super hot. It's like 29 or 28 Celsius. And I have closed the door. Let's get some juice. So, and I define few more PDF, of course. So now will I take like 10 days. Will take a whole week to read this the whole day, but I got time to do this. But I have on my old read lists. But something is new, something is updated. But let's just do it. No, it's the end of the month. I'm low on money, I have no money left, I have nothing to do. So I have to wait for Wednesday. My pension, I'll get my pension Wednesday. And day after Wednesday, Thursday, the 1st September, I have to pay my rent apartment, my bills. And there's $1,000 to my debt. So that's in like 6 days. So let's just continue. But it's 11 p.m. soon. So I did add more. Yes, we are something up here. Then semiconductor device, TS, then I did add Texas Instruments, United Microelectronics Corporation, Global Foundries, Semiconductor Manufacturing International Corporation, but that's too long title, you cannot do that on YouTube. Semiconductor Manufacturing Inc. Corp. SMIC. I find it's not be a problem with this title. Semiconductor Industries. List of semiconductor, but now I did add so many. I did have the energy to put it in the read order. So I forgot to add one. Og this Czochralski method, semiconductor device fabrication, semiconductor, this one, then all the companies there. But then we need to add all this, but I'm too tired to do this. We need to move this one, United Microelectronics Corporation, Global Foundries, and this one super long title, company name, Semiconductor Industries. Yes, this one I forgot to write down. And then a list of semiconductor plants, that's 30 pages. I forgot to write this one down. My read list, if my computer is crashing, I don't have it. So where should we put it? There. 1.295. Semi. Semiconductor chip protection. 1984. Yes, I put it up there. Now my read list is a big mess. Totally mess, like there, something there, go down to there, then go to there. Yes, then got another page. So, but let's stop to this because I have to finish something, but I always find something interesting. Yes, I have to adjust my camcorder because the tripod had moved a bit. Yes. Let's try to read this.
Czochralski method. Crystallization process of crystallization 200px.png. Fundamentals crystal times crystal structure times nucleation concepts crystallization times crystal growth. Recrystallization times seed crystal protocrystalline times single crystal methods and technology Bohr. Brigman-Stock-Barger method Van Arkelder Bohr process. Czochralski method. Epitaxy times flux method fractional crystallization. Fractional freezing hydrothermal synthesis Skiropoulos method. Laser heated pedestal growth. Micro pulling down. Shaping processes in crystal growth skull crucible. Verneuil method. Zone melting. The Czochralski method, also Czochralski technique or Czochralski process, is a method of crystal growth used to obtain single crystals of semiconductors, for example silicon, germanium and gallium arsenide, metals, for example palladium, platinum, silver, gold, salts and synthetic gemstones. The method is named after Polish scientist Jan Czochralski, 1. who invented the method in 1915 while investigating the crystallization rates of metals. 2. He made this discovery by accident. Instead of dipping his pen into high zinc well, he dipped it in molten tin, and drew a tin filament, which later proved to be a single crystal. 3. The most important application may be the growth of large cylindrical ingots, or Bohr, of single crystal silicon used in the electronics industry to make semiconductor devices like integrated circuits. Other semiconductors, such as gallium arsenide, can also be grown by this method, although lower defect densities in this case can be obtained using variants of the Brigman-Stock-Barger method. The method is not limited to production of metal or metalloid crystals. For example, it is used to manufacture very high purity crystals of salts, including material with controlled isotopic composition, for use in particle physics experiments, with tight controls, part per billion measurements, on confounding metal ions and water absorbed during manufacture. 4. Contents. Application. Production of Czochralski silicon. Crystal sizes. Incorporating impurities mathematical form. See also. References. External links. Application. Monocrystalline silicon, monoxide, grown by the Czochralski method is often referred to as monocrystalline Czochralski silicon, CZSI. It is the basic material in the production of integrated circuits used in computers, TVs, mobile phones and all types of electronic equipment and semiconductor devices. 5. Monocrystalline silicon is also used in large quantities by the photovoltaic industry for the production of conventional monoxide solar cells. The almost perfect crystal structure yields the highest light to electricity conversion efficiency for silicon. Production of Czochralski silicon. crystal of Czochralski grown silicon high purity, semiconductor grade silicon, only a few parts per million of impurities, is melted in a crucible at 1425 degrees Celsius, 2597 degree F, 1,698 K, usually made of quartz. Dopant impurity atoms such as boron or phosphorus can be added to the molten silicon in precise amounts to dope the silicon, thus changing it into P-type or N-type silicon, with different electronic properties. A precisely oriented rod-mounted seed crystal is dipped into the molten silicon. These crystals' rod is slowly pulled upwards and rotated simultaneously. By precisely controlling the temperature gradients, rate of pulling and speed of rotation, it is possible to extract a large single crystal, cylindrical ingot from the melt. Occurrence of unwanted instabilities in the melt can be avoided by investigating and visualizing the temperature and velocity fields during the crystal growth process. 6. This process is normally performed in an inert atmosphere, such as argon, in an inert chamber, such as quartz. Crystal sizes. Due to efficiencies of scale, the semiconductor industry often uses wafers with standardized dimensions, or common wafer specifications. Early on, boules were small, a few centimeter wide. With advanced technology, high-end device manufacturers use 200 and 300 mm diameter wafers. Width is controlled by precise control of temperature, speeds of rotation, and the speed at which the seed holder is withdrawn. The crystal ingots from which wafers are sliced can be up to 2 meters in length, weighing several hundred kilograms. Larger wafers allow improvements in manufacturing efficiency, as more chips can be fabricated on each wafer, with lower relative loss, so there has been a steady drive to increase silicon wafer sizes. The next step up, 450 mm, is currently scheduled for introduction in 2018. 7. Silicon wafers are typically about 0.2 to 0.75 mm thick, and can be polished to great flatness for making integrated circuits or texture for making solar cells. The process begins when the chamber is heated to approximately 1500 degrees Celsius, melting the silicon. When the silicon is fully melted, a small seed crystal mounted on the end of a rotating shaft is slowly lowered until it dips just below the surface of the molten silicon. The shaft rotates counterclockwise and the crucible rotates clockwise. The rotating rod is then drawn upwards very slowly at about 25 mm per hour when making a crystal of ruby, 8, allowing a roughly cylindrical boule to be formed. The boule can be from 1 to 2 meters, depending on the amount of silicon in the crucible. Silicon crystal being grown by the Czochralski method at Raytheon, 1956. The induction heating coil is visible, and the end of the crystal is just emerging from the melt. The technician is measuring the temperature with an optical pyrometer. The crystals produced by this early apparatus, used in an early Psi plant, were only 1 inch in diameter. The electrical characteristics of the silicon are controlled within material like phosphorus or boron to the silicon before it is melted. The added material is called dopant and the process is scald doping. This method is also used with semiconductor materials other than silicon, such as gallium arsenide. Incorporating impurities. A puller rod with seed crystal for growing single crystal silicon by the Czochralski method. When silicon is grown by the Czochralski method, the melt is contained in a silica, quartz, crucible. During growth, the walls of the crucible dissolve into the melt and Czochralski silicon therefore contains oxygen at a typical concentration of 1018 cm3. Oxygen impurities can have beneficial or detrimental effects. Carefully chosen annealing conditions can give rise to the formation of oxygen precipitates. These have the effect of trapping unwanted transition metal impurities in a process known as ghettoing, improving the purity of surrounding silicon. However, formation of oxygen precipitates at unintended locations can also destroy electrical structures. Additionally, oxygen impurities can improve the mechanical strength of silicon wafers by immobilizing any dislocations which may be introduced during device processing. It was experimentally shown in the 1990s that the high oxygen concentration is also beneficial for the radiation hardness of silicon particle detectors used in harsh radiation environment, such as CERN's LHC/HLLHC projects. 9. 10. Therefore, radiation detectors made of Czochralski and magnetic Czochralski silicon are considered top promising candidates for many future high-energy physics experiments. 11. 12. It has also been shown that the presence of oxygen in silicon increases impurity trapping during post-implantation annealing processes. 13. However, oxygen impurities can react with boron in an illuminated environment, such as that experienced by solar cells. This results in the formation of an electrically active boron-oxygen complex that detracts from cell performance. Module output drops by approximately 3% during the first few hours of light exposure. 14. Mathematical form. Concerning a mathematical expression of impurity incorporation from melt. 15. Consider the following. The impurity concentration in the solid crystal that results from freezing an amount of volume can be attained from consideration of the segregation coefficient. Segregation coefficient, initial volume, number of impurities. Crucibles used in Czochralski method. Crucible after being used. Impurity concentration in the melt, volume of the melt, number of impurities in the melt, concentration of impurities in the melt, volume of solid, concentration of impurities in the solid during the growth process, volume of melt freezes, and there are impurities from the melt that are removed. See also float zone silicon. References 1. Powell Tomaszewski, Jan Czochralski.
Yes, 70 minutes. Let's stop the video. The power is red. That was last edit, yes, last year. That's a long time ago.